The following code snippet includes the essential libraries required for handling dates, financial information, neural networks, graph plotting, and numerical calculations. Here's a breakdown of each library's role. 1. Employing data time as dth lets us handle date and time operations within Python seamlessly. 2. By importing Pandas Data Reader, data as web, we gain access to the Pandas Data Reader module, specifically the data submodule, enabling us to fetch financial data from sources like Yahoo Finance. 3. TensorFlow STF brings in the TensorFlow library, a popular choice for constructing and educating neural networks and other machine learning models. 4. Integrating Matplotlib. Pyplot as Plot lets us use the Pyplot module for Matplotlib to generate visual representations such as charts and plots. 5. Bringing in NumPy as NIP allows us to utilize the NumPy library, which is instrumental for computational tasks in Python. NumPy supports intricate mathematical operations on extensive arrays and matrices. These libraries play a vital role in our projects, aiding in tasks like retrieving financial data, crafting neural network architectures, visualizing data, and executing numerical computations effectively. Each library provides unique functionalities that streamline development processes and elevate the effectiveness of our Python scripts. Within the provided code, there are 2 variables at play. The first one, referred to as ticker, holds the string value NIDA, typically denoting a stock symbol linked to a particular company in the financial markets, in this instance, Media Corporation. The second variable, known as previous days, is set to the numeric value 1800, commonly indicating the extent of historical data one intends to review or procure. This code snippet establishes specific assignments for these variables, enabling their utilization across a program, possibly for retrieving historical stock data corresponding to the specified ticker symbol NIVDA for the past 1800 days. This dataset could serve various purposes like studying stock patterns, making projections about future stock prices, or crafting visual representations portraying the stock's performance evolution. Integrating this code enhances the efficiency in managing and preserving these distinct values for subsequent application within your program, fostering better organization and clarity. Below is a function named getPresentStockData designed to collect historical stock data for a given ticker symbol from Yahoo Finance for a predetermined number of days. Here's how it operates. 1. The function necessitates 2 arguments: ticker, the symbol of the stock, and days past, the number of days in the past, to retrieve stock data for. 2. It computes the end date by subtracting the number of days indicated by the days past parameter from the current date. 3. Utilizing the PWeb data reader method, it acquires the stock data for the specified ticker symbol from Yahoo Finance using the calculated end date. 4. Ultimately, it furnishes the acquired stock data. This code is valuable for procuring historical stock data for a specific stock symbol from an online platform such as Yahoo Finance. This functionality can be advantageous for various purposes like stock analysis, model construction, investment decision-making, or any undertaking that demands historical stock price data. This code snippet represents a function call designed to fetch stock data for a chosen ticker symbol and a defined number of previous days. It's probable that the function retrieves this data from an external source like an API or database, providing it in a format ready for additional analysis. This code snippet is instrumental in retrieving historical stock data for a specific stock within a designated time frame. This data serves multiple purposes, including trend analysis, predictive modeling, and graphical representation. It empowers us to work with current and pertinent information essential for making well-thought-out choices concerning stock trading or investment. In the given code sample, the AD close information is fetched from a data frame labeled data and stored in a variable called series. In the realm of financial analysis, AD close commonly denotes the adjusted closing price of a financial instrument, like a stock, on a particular date. These adjusted closing prices are adjusted to consider corporate actions such as dividends and stock splits, ensuring a more precise reflection of an asset's genuine value across time. By segregating the AD close data into a fresh series variable, it facilitates subsequent scrutiny, visualization, or handling of this particular dataset without modifying the primary data frame. This code excerpt comes in handy when the intention is to focus on and interact with specific columns or variables within an extensive dataset while preserving the original data and its layout. In this snippet, we have 3 variables in play. First up is test ratio, carrying a value of 0. 1. Next comes val ratio, also holding a value of 0. 1. The third variable, train ratio, steps in by subtracting the sum of test ratio and val ratio from 1. These ratios are pivotal as they help in segmenting a dataset into 3 distinct parts: a training set, a validation set, and a test set. The training set takes the lead in molding the model, whereas the validation set jumps in during training to fine-tune hyperparameters and keep tabs on the model's performance. Last but not least, the test set rolls in to assess the final model's prowess. By nailing down these ratios, data can be neatly sliced and diced to pave the way for effective machine learning model training and appraisal. Below is a snippet of code that is commonly employed to divide time series data into training and testing segments. The variable test start time is instrumental in computing the index within the series, signaling the commencement of the test data. This calculation involves multiplying the series length by the sum of train ratio and val ratio, ultimately converting it into an integer value. This approach is valuable when there's a need to reserve a portion of the data as a validation set before diving into the testing set. Conversely, the variable train end time is utilized to pinpoint the index that marks the conclusion of the training data. It achieves this by multiplying the series length by the train ratio. Such a method is crucial for the accurate delineation of the range dedicated to the training data. In essence, this code carries significance as it plays a crucial role in segmenting time series data into distinct training and testing divisions, dictating the specific start and end points earmarked for training and testing functions. The following algorithm divides a data series into multiple segments using specified time points, distinguishing between training, testing, and validation datasets by extracting date indices and values. 1. Test dates and test values represent data from the test start time onward till the series end, holding date indices and corresponding values for the test dataset. 2. Train dates and train values encompass data from the series start up to the test starting time, containing date indices and values for the training dataset. 3. Val dates and val values include data from the time point after the training dataset till just before the test dataset commences, storing date indices and values for the validation dataset. This script proves invaluable when dealing with time series data or sequences, enabling the segmentation of data into distinct sets for training, testing, and validation. It plays a crucial role in data management and organization for further analysis or modeling, particularly in scenarios like employing machine learning algorithms that mandate separate datasets for effective training and assessment. Here's a breakdown of the code snippet that generates a plot to visually represent stock data to kick things off. The first line initiates a figure, sizing it up at 15 units wide and 5 units high for accommodating the plot content. The second line executes the plotting of the training data onto the figure. It maps out the stock values against their respective dates, with train dates handling the x-axis and train values the y-axis. Proceeding smoothly, we dive into plotting the testing data on the same visual by leveraging test dates and test values to mirror the dates and stock values accurately. Adding another layer of depth, the third line brings the validation data into the mix. By assigning val dates with dates and val values with stock values, the validation data finds its rightful place on the plot. Injecting clarity into the visual representation, the script plugs in a legend to distinguish between the training, testing, and validation datasets, ensuring each dataset gets its moment in the spotlight. Following suit, the x-axis gets labeled with time to provide context for the temporal dimension, while the y-axis takes on the role of representing stock value to anchor the vertical scale. Leveraging flexibility, the title dynamically populates with the designated ticker symbol and a specific time frame indicated by the previous day's variable, presenting a concise yet informative summary of the plot's content. To culminate the plotting journey, a simple command seals the deal by unfurling the plot on the screen, laying bare the comprehensive picture of the stock data narrative. This code acts as a powerful lens through which to scrutinize and compare the stock data across training, testing, and validation datasets. By leveraging this visual aid, one can discern trends, identify patterns, and glean insights crucial for informed decision-making based on the intricate data tapestry. Here's a script that computes the mean absolute percentage error made for a basic forecast. Firstly, the code initializes a variable called naive forecast, which extracts a portion of the series data. It specifically captures data from the point located test values on positions before the series end, while excluding the value at test values. Index 1. This step effectively produces a forecast based on past data. Next, it computes the mean absolute percentage error in MAPE by contrasting the forecast generated through the naive forecast with the actual values test values. This calculation is performed using the TensorFlow function TIFF-Keras metrics. Means absolute percentage error. Subsequently, the MAPE value is converted into a NumPy array via the NumPy method. Lastly, the program displays the outcome, revealing the mean absolute percentage error for the naive forecast. This code enables us to gauge the accuracy of this simplistic forecasting technique. By utilizing the MAPE metric, we can assess how precise the naive forecast aligns with the actual test values. A lower MAPE signifies a more precise forecast. Evaluating forecasting errors is critical for evaluating the efficacy of forecasting techniques and models. This particular script is designed to compute the range of values within a specified series. Essentially, the range of a series corresponds to the gap between the highest and lowest values encapsulated in the series. By subtracting the minimum value from the maximum value, we arrive at the range of values encompassed by the dataset. This script serves as a valuable tool for swiftly assessing the extent or diversity of values present in a dataset. Such functionality proves beneficial in the realms of data analysis and statistics, enhancing our comprehension of the distribution and scope of values within a designated dataset. The function provided below serves the purpose of generating data batches tailored for training a neural network. It takes as input a series of data points, a batch size, and a window size to carry out the following operations to start. The input series is extended along a new axis utilizing TensorFlow's expandims function in order to facilitate subsequent operations. Subsequently, the extended series is transformed into a TensorFlow dataset via dataset. From TensorSlice, a sliding window size zone is constructed on the dataset by employing the window function with a shift of 1 and discarding any incomplete windows that may remain. Next, the windowed slices are flattened into individual tensors using flatmap. Each tensor is then grouped into input-output pairs utilizing the lambda_x function. The input comprises the initial window size data points in each window, with the output being the final data point. To introduce variability during training, the batches are randomized using the shuffle function with a buffer size of cleanse series 1. The dataset is subsequently batched into sets of batch size employing the batch function. Furthermore, prefetching the next batch in line is enabled to expedite the training process. Ultimately, the function proceeds to yield the generated batches, a practical method for prepping sequential data for neural network training. This technique involves segmenting the input data into windows of a distinct size to predict forthcoming data points effectively. By arranging the data into batches in this manner, the model can enhance its grasp on the sequential patterns throughout the training duration. The incorporation of data shuffling serves to deter the model from memorizing the sequence order, thereby further refining its learning process. This piece of code appears to be setting up two distinct datasets, train and val, with specific window and batch sizes. By looking at the variables window size and batch size, here's what we can gather. It seems that the function windowed is designed to generate a dataset structured into windows of a fixed size. It likely segments the data into windows that overlap, each of a length equal to window size. The dataset's train values and val values probably represent the original data that requires conversion into windowed sets designated for training and validation purposes. Respectively, the parameter batch size dictates the quantity of samples within each batch, facilitating the model training process by adjusting its internal parameters. The incorporation of windowed datasets holds significance in tasks like sequence forecasting or natural language processing. Segmenting the data into windows assists the model in grasping temporal dependencies, potentially enhancing its performance. As for the specified batch size, it aids in optimization and memory management during training by incrementally updating the model's parameters based on subsets of data rather than processing the entire dataset in one go. In this code snippet, we are constructing a neural network model utilizing TensorFlow's Keras APIs. Let's delve into the functionality of the code and the rationale behind incorporating particular elements to kick things off by employing Keras backend clear session. We are essentially wiping the slate clean of the current Keras session. This action aids in releasing memory and resetting internal states, a smart move to avert memory leaks and clashes, especially when setting up multiple models in succession. Moving on to the model creation, the model is established using the sequential API, signifying that the layers are structured in a sequential manner. Layer by layer breakdown. Keras layers convolve a standout layer in the lineup. It executes a quant convolution operation, a technique that involves applying a filter to the input data to unearth noteworthy features, particularly handy for processing sequential data like time series. Next up, we have two Keras layers, LSTM layers trailing the convolutional one. These long short-term memory LSTM units are revered for their prowess in detecting patterns in sequential data. Their forte lies in their knack for retaining and strategically revealing information over time. Keras layers dense. Here, we encounter a fully connected layer with a solitary unit at the helm, steering the ship towards churning out the model's final output. Indulging in Keras layers lambda, this element throws a lambda function into the mix, working its magic on the input in an element-wise fashion. In this instance, it's on a mission to magnify the input by a whopping 15 times the value range. This could very well be a customized operation tailor-made for the task at hand. Collectively, this code segment crafts a neural network model tailored for processing sequential data, dishing out a blend of convolutional and recurrent layers. The goal here is to equip the network with the capacity to unravel patterns from the input data and serve up a pertinent output. Embracing the right architecture and layers is paramount to ensure the model hits the mark in capturing requisite features and excels at generalizing with finesse when faced with uncharted data territories. To gain insights into the neural network model you've constructed, TensorFlow or Keras leverages the model summary function. This function offers a concise snapshot of the model's infrastructure, encompassing details like the layers, their output shapes, parameters, and the count of trainable and non-trainable parameters. This overview plays a pivotal role in comprehending the neural network's framework and proves invaluable in fine-tuning and resolving issues within the model. It enables the swift validation of the model's design, aids in identifying potential discrepancies such as mismatched input-output dimensions, and ensures that the model adheres to its intended structure. Additionally, the summary serves as a troubleshooting tool for rectifying architecture-related errors, particularly in intricate models featuring numerous layers. In the provided code snippet, we see the configuration of the training process for a neural network model using TensorFlow. Let's break down what each line accomplishes. 1. By using TIFF. Keras optimizers, learning rate of 3.9, momentum 0.9. A stochastic gradient descent optimizer is instantiated with a minuscule learning rate of 3x 10^9 coupled with a momentum of 0.9. This optimizer plays a vital role in adjusting the neural network's weights during the training phase. 2. Invoking model, compile, initiates the compilation of the neural network model, fine-tuning its training process. To finalize this compilation, an optimizer and the loss function must be defined, while optionally, one can also specify metrics for tracking progress throughout training. 3. Setting the loss function as exclusive. Keras losses, Huber ops for Huber loss, which evaluates the model's performance during training. Huber loss exhibits lower sensitivity to outliers compared to mean squared error MAPE loss. 4. The declaration metrics. Keras metrics. Mean absolute percentage error selects mean absolute percentage error MAPE as the metric for evaluation during training. MAPE gauges the percentage variance between predicted and actual values, offering insights into the accuracy of the model's predictions relative to ground truth. In essence, this code snippet plays a fundamental role in configuring the training process for a neural network model by defining the optimizer, loss function, and evaluation metrics. These elements are pivotal for effectively training a model and monitoring its performance as it progresses through the training regimen. In the realm of TensorFlow Keras, this code snippet showcases the employment of callbacks, a set of functions that come into play at particular junctures during training. Model checkpoint is the first callback in action here. It functions by safeguarding the model's weights under specified circumstances. In this scenario, it's earmarked for storing the optimal model judged by the validation loss in a file denoted as checkpoint. 5. Moving on to early stopping. This callback halts the model training when a monitored metric, like the validation loss, ceases to show progress. If the validation loss fails to decrease by more than 0.1 after 50 epochs, the training halts. The reset states callback introduces a custom callback that is an extension of TIFF. Keras callback. Its task is to reset the model states at the genesis of every epoch. This proves beneficial when dealing with stateful runs recurrent neural networks where adept state management is pivotal for preserving memory across different time phases. Callbacks play a pivotal role in the domain of deep learning by tailoring the training procedure, securing the finest model, circumventing cover-fitting through early stopping, and managing peculiar scenarios such as state resets. They furnish a channel to intervene in the training cycle for refining model efficacy and streamlining the training process. In this snippet of code, a long short-term memory LSTM model is trained on the dataset for 1,000 epochs. Throughout the training phase, the validation data is leveraged to assess the model's efficacy. Moreover, various callbacks like model checkpoint, early stopping, and reset states are incorporated. Here's a breakdown of the aforementioned callbacks. The model checkpoint function saves the optimal model weights based on specified criteria, typically focusing on validation loss. As for early stopping, it evaluates a designated metric e.g., validation loss, and halts the training procedure prematurely if the metric shows no further enhancement. Lastly, the reset states callback resets the internal states of the LSTM cells between batches to mitigate potential challenges related to vanishing or exploding gradients inherent in RINs. These callbacks play a pivotal role in enhancing the LSTM model's performance and robustness during the training phase. They facilitate the preservation of the finest model version, counteract overfitting tendencies, and ensure the LSTM cell state remains appropriately calibrated. Utilizing the Matplotlib library, this code snippet generates a visualization depicting the mean absolute percentage error MAPE values for training and validation sets while training a long short-term memory LSTM model. To break down the code execution: 1. A figure is initialized with dimensions set to 12x5 units. 2. By employing the pulled semology function, a semolog plot is created, utilizing a logarithmic scale for the axis. 3. The training MAPE values, accessed from the means absolute percentage hierarchy of the list history object, or plotted. 4. Correspondingly, the validation MAPE values retrieved from the val means absolute percentage hierarchy of the list history object. or plotted. 5. Axis labels are assigned epoch for the x-axis and absolute percentage error for the y-axis. 6. A legend is included to distinguish between the training and validation data. 7. The plot title is designated as training and validation mapes. 8. Finally, the plot is exhibited using pult show. This code proves invaluable for assessing the LSTM model's progression across epochs. By visualizing MAPE values for training and validation datasets, one can track the model's advancement and its ability to generalize effectively. Analyzing the trends in MAPE values visually aids in understanding the model's performance, recognizing signs of overfitting or underfitting, and ensuring optimal training outcomes. This snippet of code appears to be a component of the evaluation process for a machine learning model. The variable list history and absolute percentage error appears to hold the values of the mean absolute percentage error metric for the validation dataset while an LSTM long short-term memory model is being trained. The purpose of employing the min function is to pinpoint the smallest value within this collection of mean absolute percentage errors. Spotting the minimum validation error is crucial for pinpointing the optimal model based on this specific metric. Smaller values of mean absolute percentage error signify enhanced model performance and prediction accuracy. Hence, opting for the model that exhibits the lowest validation error is typically preferred. Through this code, we can accurately single out the model with the most minimal mean absolute percentage error on the validation set, a pivotal step in identifying the most adept model for achieving precise predictions. The provided code snippet is designed to import a pre-trained TensorFlow model saved in a file called checkpoint. 5. This model likely underwent training on an extensive dataset for a particular purpose, like categorizing images or analyzing sentiments. Employing this code allows us to leverage the pre-existing model to predict outcomes on fresh data or further train it with new information. Reusing a pre-trained model proves advantageous as it cuts down on the time, computing power, and work needed to build a model from the ground up. Consequently, the model stands ready to deliver prompt prediction sans the necessity of retraining. The function called enthusiast is crucial for generating forecasts based on a designated model for time series data. Let's delve into how this code operates. First and foremost, it necessitates three key inputs to model the pre-trained machine learning model employed for predictions. Series: the time series dataset intended for forecast generation. Window size: the specified window size utilized for data sequence creation. To commence, a TensorFlow dataset named indices is formulated from the provided series. Subsequently, a windowing method is applied to the dataset with a window size and a shift of 1, thereby producing a series of windows of the set size traversing the dataset. The subsequent step involves consolidating the dataset by grouping the window data into segments of window size. Further streamlining the process, data is grouped into sets of 32 to boost efficiency, and data prefetching is incorporated to optimize data loading. The model at hand is then leveraged to project forecasts for the data batches. Ultimately, the resultant forecast generated by the model is returned. This code stands as a cornerstone for leveraging machine learning models to predict outcomes for time series data, with a specific focus on TensorFlow through data batching, windowing applications, and prefetching strategies. It streamlines the handling of large datasets and the production of forecasts. The following code snippet demonstrates how to utilize a trained LSTM model to make predictions on a time series dataset. Let's delve into a breakdown of the code's functionality to begin with. The enthusiast function is invoked with the trained LSTM model, the time series data represented as a tensor with an added dimension, and the window size as parameters. This function serves the purpose of generating predictions by leveraging the model and the provided input data. Subsequently, the enthusiast variable is initialized by slicing the predictions array to extract the projected values commencing from test start time window size up to the penultimate element within the array. The final element's specific value within the array is accessed by utilizing index 1 for the first dimension, 1 for the second dimension, and 0 for the third dimension. Furthermore, a matplotlib figure is generated with specified dimensions. The actual and anticipated values are then visualized on a shared graph employing pult. Plot: the x-axis corresponds to the date's test dates, while the y-axis represents the stock values. For enhanced comprehensibility of the graph, the key label is designated as date, and the A label is denoted as stock value. Additionally, the actual stock values test values are overlaid on the same graph for juxtaposition with the LSTM model's prognostications. A legend is incorporated into the plot to differentiate between the actual and predicted values. The title of the plot is customized to incorporate the ticker symbol and signify that it displays genuine and projected prices for the specified stock. Lastly, the plot is showcased utilizing Pult Show. The primary objective of this code is to visually display and contrast genuine stock values with the estimations generated by the LSTM model. This visualization aids in evaluating the model's performance and understanding its ability to predict future stock values based on historical data accurately. Conducting a visual examination and validation of the model's predictions is crucial to ascertain its precision and effectiveness in delivering trustworthy forecasts. The purpose of this script is to determine the mean absolute percentage error made between two arrays, known as test values and enthusiast, leveraging TensorFlow's metric for mean absolute percentage error. MAPE serves as a gauge of accuracy in model predictions, analyzing the percentage variance between forecasted values enthusiast and actual values test values. MAPE stands as a fundamental measure for assessing the effectiveness of predictive models, notably utilized in evaluating models such as LSTM long short-term memory neural networks. Its value lies in offering a more relatable assessment of prediction precision when juxtaposed with alternative metrics like mean squared error maze, as it denotes error percentage in relation to factual values. Adopting this code equips us to objectively evaluate the LSTM model's efficacy in foreseeing the test data, presenting the margin of error in a simple, percentage-based manner. This facilitates seamless comparisons of accuracy between various models or the same model across diverse scenarios. The provided code seems to be setting up training and validation datasets utilizing a method known as windows. It seems that the windows function likely changes datasets containing train values and val values, along with parameters like batch size and window size. This function appears to divide the dataset into windows of a specified size and groups them into batches of a certain size. Such data preprocessing techniques are widely applied in machine learning scenarios like time series forecasting or sequence prediction to segment data into smaller units for training and validation endeavors. This practice aids in correctly structuring input data to enhance the efficiency of model training. In essence, the code is priming the data for training and validation purposes, segmenting it into batches and windows, a customary preprocessing step in the realm of machine learning. In this snippet, the variable num on blocks is set to 6. Assigning a specific value to a variable like this is crucial for storing and accessing that value efficiently. By utilizing such variable, we streamline referencing the value 6 in our program by simply using num on blocks. This approach enhances code readability and manageability, since altering the value later on only requires adjustments in one location, the assignment statement. In this code snippet, the following actions are executed. Firstly, it resets the current Keras session to release memory resources. Next, a sequential model is established under the name on model. Subsequently, an input layer is incorporated into the model with a shape of none. 1. Following that, a sequence of convolutional layers is appended to the model within a loop, each utilizing distinct dilation rate values. This parameter dictates the spacing between elements within the convolution filter. Moreover, specific settings for the convolutional layers are configured, encompassing the number of filters, kernel size, activation function, and other attributes. Lastly, a final convolutional layer with a solitary filter and a kernel size of 1 is injected into the model. The objective of this code is to devise a profound convolutional neural network CNN model employing dilated convolutions. Dilated convolutions prove advantageous in capturing extensive dependencies and sequential data while minimizing the escalation of parameters within the model. By iterating through the num on blocks, one can conveniently fine-tune the network step by altering the quantity of dilation rates employed in the model. The summary function in Keras is quite handy as it gives a neat rundown of the model setup, covering details such as various layers, their types, output shapes, and the parameter count in each layer. This kind of info comes in clutch when delving into the nuts and bolts of a neural network model. By glancing at the summary, we can swiftly size up a model structure, verify layer connections, and scrutinize the parameter count, which clues us in on the model's intricacy and flags potential hiccups like overfitting. All in all, this model summary offers a bird's-eye view of the neural network, serving as a useful aid throughout the model development and debugging phases. Within the code snippet provided, the setup entails configuring an optimizer, a loss function, and metrics for a convolutional neural network CNN model crafted using TensorFlow's Keras API. To begin, we are applying stochastic gradient descent D as the optimizer with a designated learning rate of 4.6 and momentum value of 0.9. This choice aids in enhancing the model's training efficiency by iteratively adjusting weights based on computed gradients. Moreover, the loss function is defined as Huber loss, a robust choice that exhibits lower sensitivity to outliers in the data compared to mean squared error maze. This characteristic ensures a smoother training process, particularly when confronted with noisy datasets. Furthermore, the model's performance is assessed using the mean absolute percentage error MAPE metric during the training phase. This metric gauges the percentage variance between predicted and actual values, proving beneficial for regression tasks, particularly in scenarios where the target variable scale widely fluctuates. Through the calibration of these elements, we are establishing the CNN model to undergo training using CD optimization, alongside the designated loss function and evaluation metric. These selections play a pivotal role in outlining the training methodology, optimization objectives, and performance assessment criteria throughout the training procedure. In this TensorFlow code, a callback function is being established, namely a model checkpoint callback, with the intention of preserving the model's weights while it undergoes training. The setup here entails specifying that only the most optimal model achieved throughout the training, based on a chosen metric such as validation loss or accuracy, will be saved. These saved checkpoints of the model are housed in a file called checkpoint. 5. Throughout the training phase, this callback diligently evaluates the model's progress, ensuring that the model's weights are recorded in the designated file whenever a new superior outcome is attained. This functionality proves to be quite advantageous as it guarantees that in scenarios where the training process is halted abruptly or there's a desire to utilize the top-tier model crafted during training, one can effortlessly restore the model from the stored checkpoint without the necessity of reinitiating the training process from square one. Such a feature becomes particularly invaluable for protracted training sessions where it becomes imperative to keep tabs on the most outstanding performing model. In this script, the fit method of a conversation model is deployed to train the model on the training data train over 500 epochs. The validation data val is leveraged to assess the model's performance throughout the training phase and guard against overfitting. The callbacks parameter plays a pivotal role by specifying a series of callback functions that get invoked during the training process. For instance, the model checkpoint callback is utilized to retain the model that demonstrates optimal performance on the validation set. Additionally, the early stopping callback intervenes to halt the training process if the model's validation set performance stagnates over a specified number of epochs. The inclusion of the reset states callback seems geared towards refreshing the model's internal states between epochs. Employing callbacks of this nature yields enhanced training outcomes, encompassing artifact preservation, overfitting prevention, and maintenance of state integrity. Such code is imperative in orchestrating an effective training regimen for the conversation model, ultimately refining its efficacy for applications such as chatbots or question answering systems. Below is a script snippet that leverages matplotlib to craft a plot and showcases it using Bolt. The snippet initiates a figure set to specific dimensions 12 inches in width and 5 inches in height. Proceeds to plot two lines on a semi-logarithmic scale. This comparison aims to analyze the mean absolute percentage error values concerning both training and validation data across various epochs. The x-axis is denoted as epoch, while the y-axis is named absolute percentage error. Moreover, a legend is integrated to distinguish between the training and validation lines, and a title is assigned to the plot. This piece of code proves instrumental in visually assessing and contrasting the evolution of mean absolute percentage errors within a model throughout its training and validation stages. Its purpose lies in aiding the comprehension of the model's performance and determining potential overfitting or underfitting occurrences based on the log training and validation errors. This snippet of code is designed to locate the smallest value within the list of validation mean absolute percentage errors. Val means absolute percentage error extracted from the training history of a neural network model. Within the ONV history object lies a collection of metrics recorded throughout the training process, with our focus zeroing in on pinpointing the minimum value of the validation mean absolute percentage error. This script serves as a valuable tool for assessing the neural network model's performance as it trains, enabling the identification of the optimal model based on validation metrics. Through identifying the epoch associated with the lowest validation error, we can pinpoint when the model excelled the most with the validation dataset. This insight holds significant value for tasks such as model selection, fine-tuning hyperparameters, and closely monitoring training advancements. In this code snippet, a pre-existing machine learning model is imported from a file called checkpoint. 5. Using TensorFlow's Keras tool, the clone model function is employed to retrieve a model that had been saved during an earlier training session. Taking advantage of a pre-trained model comes in handy when you aim to recycle a model for prediction making, analyzing fresh data, or advancing its training. This approach helps you skip the laborious training phase and tap into the wisdom already ingrained in the model. Embracing a pre-trained model lets you leverage the groundwork laid in training the model for a particular task or dataset. This strategy conserves your computational power and time by capitalizing on prior model training efforts. This snippet of code appears to be a segment from a project related to machine learning or time series forecasting. probably centered on predicting stock prices through a convolutional neural network model conv model. Let's delve into the functionalities of the code 1. It employs the onv model to make predictions on the input time series data series via the model first function. 2. It filters out the forecasted values for a specific time frame from test start time window size to the second last element and isolates the relevant stock value predictions 1, 0, 3. Subsequently, it creates a plot illustrating the projected stock values matched with the corresponding test dates using matplotlib. 4. The plot showcases the actual test values to facilitate a comparison. 5. As a finishing touch, the code titles the axis, incorporates a legend, and provides a title for the plot before displaying it with pult. Show visualizing the predicted stock values in comparison with the actual values is imperative for assessing the accuracy of the stock price predictions made by the model. This visual representation allows for a direct assessment of the model's predictive alignment with the real stock values, offering valuable insights into the model's efficacy and potential areas for enhancement. Additionally, it aids in recognizing trends and patterns within the data, which can inform decisions related to trading or investment strategies. The provided script is designed to determine the mean absolute percentage error MAPE for a regression task employing a deep convolutional neural network CNN model. MAPE is a widely used metric for assessing the precision of a model's forecast in terms of percentages. Initially, the code utilizes a TensorFlow function, TIF, Keras, metrics, mean absolute percentage error values, on forecast, to compute the mean absolute percentage error linking the actual values test values and the predicted values on forecast arrays, to transform the result generated by the mean absolute percentage error function into a NumPy array. The NumPy method is applied. Subsequently, the script presents the MAPE value in a well-formatted string leveraging infstring, ensuring a lucid and easily readable display of the MAPE outcome. In essence, this script evaluates the MAPE for the forecasts produced by a deep CNN model, offering insights into the model's performance by quantifying the average percentage error in its predictions. The process of computing and monitoring the MAPE is crucial for assessing the model's precision and pinpointing areas necessitating enhancement. This code snippet seems to be carrying out a logical evaluation between two variables or values. The expression conv_MAPE and MAPE is essentially checking if the value held by conv_MAPE is smaller than that of nMAPE. If it turns out that conv_MAPE is indeed less than nMAPE, then the outcome of this assessment will be true. If not, it will be false. Such comparisons are quite typical in programming for making decisions based on how variables or expressions stack up against each other. In this particular instance, it appears to be utilized to ascertain whether one mean absolute percentage error MAPE value is less than another MAPE value. This kind of insight can prove valuable in a variety of situations, like evaluating forecast accuracy or comparing the efficacy of different models or algorithms.